marks cards.
So thanks a lot, Christoph. So today I'll be telling you about sublinear time approximation algorithms to beat one-half approximation factor for the max cut problem, bounded degree graphs. So this appeared in iCal this year. It's joint work with Agastya Jha, who will start a PhD at U Chicago. And I also must thank Michael Kapralov for early discussions on this project. All right, so let's get started. So I'd begin by reminding you what the max cut problem is. Okay, right, so this problem, you're given as input a graph. So for me, the graphs in this talk will always be bounded degree. And for simplicity, let's assume that the graphs are in fact d-regular for some constant d, right? So you're given some d-regular graph, and what you would like to do is you would like to split its vertex set into two subsets such that the number of edges which go across is maximized. So that's the max cut problem, which you know and love. So for instance, in this picture, like the maximizing bipartition is in fact this bipartition. And just some notation, I'll denote by MC of G, the fraction of edges that are cut by the maximizing bipartition. Okay. So since I'm going to be talking about sublinear time algorithms, I should specify what query model I'm using. So the query model is in fact the adjacency list query model. So let's see what kind of queries you're allowed. So you can ask for a vertex query. So here you ask that, okay, give me a random vertex, and I'll give you some random vertex, like that red vertex there. And you can also ask for a random neighbor query, right? So you can ask that, okay, there is some vertex I, and give me like, you know, the fifth neighbor of vertex I, something like that. And that's what I would do, right? Or some random neighbor of this vertex, right? I'll give you some random neighbor. Okay, so what this facilitates is that it allows you to explore the graph by crawling along its edges. All right. Okay, and the question that I'm interested in is the following, that of course, I cannot hope to find the maximizing bipartition entirely in sublinear time. So the question I'm instead asking is the following, that, you know, I give you this graph, and please tell me whether the cut value is close to 1 or whether the cut value is close to 1/2. Okay. So if the problem statement is clear, okay, right? Is the cut value close to 1? Is it close to 1/2? All right. So let me now just recap briefly about a bit of history on this problem. So if you are interested in a factor 1/2 approximation, that's trivial. You don't have to make any queries. You just say that, you know, I am already aware that I can cut 1/2 fraction of the number of edges that sit inside this graph. All right, then Ashish Shiplankar, Michael Kapralov, Sanjeev Khanna, Aida Musawifar, and Yuval Peris in Fox 2018, they showed that, if you want to get slightly better than 1/2 approximation algorithm, then you must pay strictly more than root and time, right? So in order to get a half plus epsilon approximation algorithm, you must spend n to the 1/2 plus omega epsilon queries, right? Okay, and it was this paper that, assured this question to the front lines of research in sublinear time algorithms, that can I get better than 1/2 approximation in sublinear time, all right? So the question was, can you do this for some interesting graph classes? Then Pan and Yuichi Yoshida showed in Soda 23 that yes, you can do this on expanders. Right, and the content of this work is that you can in fact do this on a much more general family of graphs, the so-called clusterable graphs. All right, so super briefly, so I will formally define what clusterable graphs are. I'll remind you what expanders are. But like clusterable graphs, you should think about it in the following manner, that it's a graph in which you have some vividly visible clusters. You can partition the vertex set into these vividly visible clusters, which for instance are these bubbles over here. So now let me formalize what clusterable graphs are, and I do that by first reminding you what expanders are. So I'm given some d-regular graph, and I consider like some way of partitioning the vertex set into two subsets, S and S complement. Let's call S to be the smaller side, the side that contains fewer than half the vertices. And expansion, is just a notion of connectivity. All right. So it tells you that the graph is hard to disconnect, because in order to disconnect the smaller side from the bigger side, in order to disconnect S from complement of S, the fraction of edges you are going to delete is a lot. So you should think of expansion of S being at least some constant, right? So if all small sets have this property, I call the graph an expander. Okay. And now I'm ready to define clusterable graphs. First, I need to make one more definition. I need to tell you what a cluster is. So a cluster for me is going to be a notion of expansion for some vertex-induced subset. So I have some vertex-induced subset, capital C over here, and given a subset S of this set, capital C, I define its inner expansion to be the following quantity. It's the number of edges that go from S to the set C minuses. So S to rest of the vertices within this bubble, normalized by the minimum of the two volumes. Okay? And for deregular graphs, this notion just boils down to, I have D times the size of S and D times the size of C minus S in the denominator. All right? And if all subsets S of C have large inner conductance, I call this subset of vertices to be a cluster. Okay. And now finally, I'm ready to define clusterable graphs. By the way, are there any questions at this point? All right. So let me move ahead. Yes.
Cluster, you don't have.
Good point. That's a good point. So I'm normalizing by the volume in the original graph. Like there are reasons to do that, but like for deregular graphs, you can imagine that these two notions will be in constant factor of each other. So that's a good point, though. But yeah, I don't want to get into that. Yeah. All right. So now let me tell you what clusterable graphs are. So I call a graph G to be k phi epsilon clusterable if you can partition its vertex set into k disjoint subsets, all of which have large inner conductance, and they continue to have small outer conductance, where outer conductance is the standard notion of conductance you're familiar with. All right. And here the parameter regime I'm interested in is the following. So this inner conductance is at least some constant, and the outer conductance is something sufficiently small, some tiny little epsilon. All right. So that's the parameter regime I'm interested in. And my goal is to try and understand whether I can beat one-half approximation for max cut on this family of graphs. All right. So let's begin by recapping the k equals 1 case. This is just the expander case, right? And this is the algorithm that Pan and Yuichi had, like in Soda 23 last year. And the question was like precisely this thing, that decide for me whether the cut value is at least 1 minus gamma or whether it's at most 1/2 plus gamma. All right. So let's introduce some notation first. So I will denote by PVL the endpoint distribution that you obtain after performing an L-step long lazy random walk that starts at the vertex V. Okay. And think of the parameter L as being log n over the conductance squared. Okay. All right. Then what their algorithm does is the following, that it picks some initial vertex and it samples an L-length random walk from the start vertex and call this lazy walk W. Now what you do is that you erase all self loops from W and you end up with a loop erased walk W prime. What Pan Peng and Yuichi should recommend is that you should look at the length of W prime. So if the length of W prime is an even number, so imagine the following situation, that suppose my graph was truly bipartite. And suppose the walk begins at a vertex on the left side. If W prime is in fact an even number, you are back to the left side. If W prime is an odd number, you are on the other side. All right. So what they observed in particular is that, look, in this situation, the distribution when the length of the walk W prime is an even number, it's supported on the left side. And in the situation where the length of the walk is an odd number, W prime is an odd number, this is supported on the right side, right? So these two distributions, they end up fairly far. Okay. And turns out that this intuition survives in the situation when the cut value is in fact very close to 1. So if the graph is nearly bipartite, these two distributions continue to remain far. Right? So what they recommend is that you should use the following indicator as a reliable indicator for the cut value. That if the L2 squared distance between these two distributions is large, you should say that the cut value is large, it's close to 1. On the other hand, if this value is small, you should conclude that the cut value is in fact close to 1/2. All right? It's a pretty elegant analysis, a beautiful paper. And yeah. Okay. So let's try to now think about what happens when k is greater than 1. So unfortunately, this analysis does not continue to apply in this situation. In fact, even for k equals 2, this analysis breaks down. Let's see why. So suppose I'm given the following graph. I'm going to present the graph piecemeal. So I'm going to be constructing a graph with cut value being really close to 1, and I'll show you what kind of problems arise. So imagine the following situation that, so for simplicity, imagine that gamma, the cut value parameter, is at most epsilon, or like theta of epsilon, like 10 epsilon or something. All right. So in this situation, let's consider the following instance. So I have two isomorphic bipartite graphs two isomorphic regular bipartite graphs where the regularity parameter is 1 over epsilon minus 2. Okay. Now what I do is that I connect the vertex subset A1 with A2 via a perfect matching. And I also connect the subset A1 with B2, again via perfect matching. I just add all matchings, like B1 to B2, B1 to A2. All right. And like you can see that like this graph is now it has like large cut value, but the Peng-Yoshida idea, like it unfortunately fails now, because if you perform a walk of length of logarithmic length, then an expectation in every 2 or epsilon steps, the walk reverses its polarity. So now you can no longer get that distance between the odd and even step distributions as a reliable indicator. All right, so some new ideas are needed. So let's see what one can try. So to start off, let's consider the following different intuition. So imagine the following situation that look, I give you this graph. And so suppose it's an expander. Suppose it's an expander graph. And there are, so I should connect them by, so there are enough edges running between these two subsets. Imagine performing a two-step non-lazy random walk. What will happen? So if you start on the left side, you're back on the left side. Start on the right side, probably back on the right side. And the idea is that suddenly two new sparse cuts emerge. So suddenly you have one expander emerging induced on the left subset, another expander emerging induced on the right subset, and they are connected sparsely. All right. So this is the idea that underlies the rest of the talk. The key thing is that, if my graph in fact had this property that the cut value was truly large and it was an expander, then more sparse cuts emerge. All right. And I could use this information about more sparse cuts emerging to obtain a tester. Right. So let me detail that now. So in fact, if you had C-induced clusters with large induced cut value, then you can show that a similar analysis should suggest that you will get K plus C sparse cuts. All right. So the rest of the idea is to, in fact, track the K plus Cth eigenvalue of some appropriate Laplacian. And that's what I would do in the rest of this talk. All right. So let's move on. Okay, so the main theorem that we show in the paper is the following, that there is an algorithm which essentially does the job. So if you give this algorithm as input, a k-phi epsilon clusterable graph, which I assume to be deregular for simplicity, this algorithm has this funny runtime, n to the 1/2 plus some big O of epsilon, and it returns the correct verdict with good probability, the correct high-low cut value verdict with good probability. All right. This O star notation hides some poly k terms and some polylog n terms. Okay. Any questions so far? Okay, so let's move on. So let me begin by recapping the approach that I highlighted once more. So the key idea would be to understand the spectra of the high cut value instance and the low cut value instance. We'd like to show that the spectra, they are appreciably different. And we would like to exploit this appreciable difference in the spectra towards obtaining a tester. And we would show that this spectra is so appreciably different that a sublinear time procedure, a sublinear time random walks-based procedure, can figure this difference out. Okay. Right. So I want to begin with a tiny little note. So suppose your cut value is really large, your graph is partitionable into k clusters. Right. Then what you can show is that there is a good number of these clusters, at least 2k over of 3 of these clusters, whose induced cut value is truly large. It's at least 1 minus big O of gamma. And in the other case, when the cut value is close to 1/2, what you can show is that, again, there are enough number of these clusters, at least 2k over 3 of them, whose induced cut value is at most 1/2 plus big O of gamma. Okay, so let's start now. So here is the algorithm. So I start off by assigning this parameter C, the eigenvalue that I want to track, this k plus Cth eigenvalue. I start by initializing that parameter C to be 2k over 3. I choose a number of samples I'm willing to pick, and this number of samples is just poly k times sum into the epsilon. The poly k factor is there just in order to hit every single cluster. Okay. I initialize some appropriate walk length, log n over the conductance squared, And now the entire idea is that I compute this littlest by littlest matrix, this gram matrix of collision probabilities. Right? Okay. So I compute this littlest by littlest matrix, and then I just check some appropriate eigenvalue of this matrix of collision probabilities. If this rescaled eigenvalue of that, if this k plus cth eigenvalue after rescaling is large, you should conclude that the cut value is large. Otherwise, you conclude that the cut value is small. And this matrix you can in fact compute it efficiently. You just you can do this by just doing some collision counting, and you can do that with pretty good approximation, like 1 over n to the 1.01 kind of approximation. Okay, so let's see why this algorithm should work. Okay, so this is going to be a very high level overview. So what you can show is that so on the previous slide, I had this m to the t times s. So let's suppose what happens when this s is in fact identity. Okay. So if the cut value is really large, what you can show is that the k plus cth eigenvalue of m to the 2t is going to be really large. It's going to be at least 1 minus epsilon to the 2t. And on the other hand, when the cut value is small, you can show that this k plus cth eigenvalue is appreciably small. And let's just make sure that we understand what this parameter setting means. So you can quickly verify that, this quantity, 1 minus epsilon to the 2t, it's at least e to the negative 4t times epsilon. And by just plugging in the value of t, the length of the walk, what you get is that in this particular situation, this quantity, the k plus cth eigenvalue, comes out to be large enough, like n to the negative epsilon, comes out to be of the correct order. In the other situation, if you believe claim 2, what will happen is that again, you plug in the parameters, you plug in t to be log n over phi squared, the phi squares cancel off, and you see that this quantity is sufficiently small. Right? Okay, so now I would like to give you some intuition behind claim 1 and claim 2. So for claim 1, the key idea is something like the following, that my graph is k clusterable. Okay, so I already know that if I look at the Markov matrix, I have to have k eigenvalues, all of which are close to 1. So I have k eigenvalues that are close to 1. On the other hand, I also knew that I have 2k over 3 clusters that are almost bipartite. Okay, I have 2k over 3 nearly bipartite clusters. So this gives me a bunch of eigenvalues, at least c of them, that are close to negative 1. So I have k eigenvalues close to positive 1, c eigenvalues close to negative 1. If I look at an even power of this matrix, what I would have is, I conclude that there are at least k plus c eigenvalues of m to the 2t, all of which are at least 1 minus 10 epsilon to the t. Okay? Right? So this is the intuition behind claim 1. Now let's see intuition behind claim 2. By the way, any questions so far? Oh, because I'm told that the cut value of the graph overall is really large. It's a k clusterable graph. So you can split the vertex set into k expanders sparsely connected with each other. And you should really think that these clusters roughly have the same size. So that point I did not stress. You should imagine that the k clusters have roughly the same size. Okay. Any other questions? Let's move on. So now let me give you some intuition behind claim 2. So the key idea here is something like this, that here we prove an interesting spectral lemma. If I have time, I will delve into the proof. What you can show is that in a spectral expander, the n minus 1th eigenvalue of the Markov matrix, it's bounded away from negative 1. The n minus 1th eigenvalue is bounded away from negative 1. It's an intuitive fact, but somehow seems to be new in spectral graph theory. And what you can show is that, since so you should pretend that, I was given this k clusterable graph. You should pretend that these k clusters, they're kind of isolated from each other. There are no cross edges running between them. In this situation, if you look at the eigenvalues of the overall Markov matrix, it's going to be union of eigenvalues of all of these isolated pieces. And this will tell you that, I have at least k eigenvalues, all of which are bounded away from negative 1. Then again, you get c eigenvalues, other c eigenvalues that are bounded away from negative 1, because all of these clusters, their cut value is close to 1/2. So just by like running Trevisan's algorithm, or there are lots of other ways to conclude this. You can show. So Pan and Yuichi also had this analysis in their paper using bipartite ratio, some appropriate analysis of Trevisan that if my cut value is close to 1/2, then the biggest eigenvalue is bounded away from -1. So again, this gives you C eigenvalues bounded away from -1. Step 1 gives you K eigenvalues bounded away from -1. You put the two together and you conclude claim 2. All right. So what I have shown so far is what happens for the eigenvalues of the matrix M to the 2t or M to the t times S, where S was identity. Algorithmically, you are looking at some subset S of vertices, right, which is kind of smallish. So what do you do now? So the key idea then is to just Hale matrix Bernstein. The idea is to just show some appropriate two-norm bounds on the probability vector that you end up with after a t-step walk from any given vertex. And the way you show this is, you write this vector, the indicator for x, in the eigenbasis, and you can split it up into these two sums. So the first sum is referring to those eigenvalues that are close to 1 in absolute value. The other term refers to those eigenvalues which are sitting away from 1 in absolute value. And this term just runs off to 0. And for that term, you can establish some L infinity norm bounds on this vector, on the eigenvectors. So you can prove L infinity norm bound on eigenvectors. That's a beautiful argument in a paper by Grzegorz Gluck, Michael Kapralov, Silvio Lotanzi, Aida Mosavifar, and Christian Soler. Okay, so if there is interest, I can tell you the proof of that spectral claim. So should I prove that? Okay, so let me show the proof of that spectral claim. So the deferred claim essentially postulates the following, that if the n minus nth eigenvalue of the Laplacian is close to 2, then the second eigenvalue, lambda 2, is at most big O of epsilon. Lambda 2 is small. So there was some previous argument also that could prove a statement of a similar flavor. That's kind of like rerunning higher order Shiger inequality on the upper side of the spectrum, but that loses square roots. So you can only conclude that if lambda n minus 1 is at least 2 minus epsilon, lambda 2 you get is at most square root epsilon. So this is an improvement. All right, and another way to understand what this claim is telling you the following, that in a spectral expander, lambda n minus 1 is sitting comfortably away from 2. Okay? Because lambda 2 is a constant. So yeah, that's what you get. All right, so let me try to sketch how we prove this. So the idea would be to at a cartoon picture level, let's start with the following picture. So suppose I have a graph which consists of two disjoint bipartite graphs. So this bipartite graph is, I have two disjoint bipartite graphs. And what you can do is that you can immediately start writing some eigenvectors. So here is eigenvectors with eigenvalues 2, right? So I'm writing out some eigenvectors with eigenvalue 2. The first eigenvector is xi, which is supported only on this set. It's -1 over root n over a1 and +1 over root n over b1. The other eigenvector is yi, which is supported only over this set, -1 over root n here, +1 over root n there. So imagine doing the following process. Look at the vector yi and just change this thing to a plus. And suddenly I have arrived at a vector whose Rayleigh quotient is very small. Right? It's just the constant function. So the Rayleigh quotient is small. All right, so I can do a similar process over here. And what this gives me is two disjointly supported vectors, orthogonal vectors, both with small Rayleigh quotient. And this proves for me that indeed for this special instance, lambda 2 is small. But I can't expect such an analysis to work in general, right? So let's see what you can do in that situation. So the idea would be something like the following, that give me any vector z whose Rayleigh quotient is close to 2, whose Rayleigh quotient is at least 2 minus epsilon. And now consider the following vector z prime, which is obtained by taking absolute values of z in every single coordinate. It's a 1-minute verification that this vector z prime has a small Rayleigh quotient. This Rayleigh quotient is in fact at most epsilon. That's a immediate verification. All right, and now the rest of the idea in the argument will be the following: that okay, I will start with this observation, and what I would like to do at the end of the day is that I'd like to produce two vectors x and y, both of which have a small Rayleigh quotient. That's what I'd like to do. Okay, make sense? Yeah. All right, so the choice for x is kind of obvious. There is this vector that's kind of standing out, that hey, pick me, the all ones vector, or the all ones vector normalized to have unit length, which is 1 over root n in every single coordinate. For the vector y, I'm wondering if I could pick y to be this vector z prime, where z is some vector with large Rayleigh quotient. Can I pick y to be z prime? Unfortunately, no, because y is positive in every single coordinate, and it could be highly correlated with the all ones vector. That does not look like a right choice, but that's almost the right choice. It suggests what the right choice should be. So maybe I could choose y to be the vector z prime minus this component of z prime along the all ones vector, all ones over square root n. When I say all ones, I mean the unit vector along all ones. But again, there is this annoyance that the Rayleigh quotient of y might shoot up. So I'll call such a vector z that you start with to be a bad vector. Right? I'd like to show that there are good vectors. Okay. The entire idea in the rest of the argument, so I remind you here what a bad vector is. So the vector y that I end up with is bad if the Rayleigh quotient of y is large, or equivalently, the 2 norm of y becomes super small. So when can the 2 norm of y become super small? It becomes super small when z prime is highly correlated with the all ones vector. You subtract the component along all ones, and boom, the length of y becomes super small, and your Rayleigh quotient shoots up. All right. So in this situation, since z prime is highly correlated with all ones, z prime should have a large L1 norm. It's 1 over root n, around 1 over root n every single coordinate. So it has a large L1 norm. Okay. So suppose you're looking at the last two eigenvectors as in Rayleigh quotient close to 2, right? And suppose they are both bad. If any of them is good, you are already done. Suppose they are both bad, then what you can show, so bad vectors, they will look something like the following. So Vn minus 1, it will be negative 1 in a bunch of coordinates, positive 1 in the other bunch. Similarly, Vn, it's negative 1 over root n's, right? It's negative 1 in a bunch of coordinates, positive 1 here. Now, if you take some appropriate combinations, namely that combination, just obtain a unit vector by taking a 45-degree combination of these vectors, what you will show is that this vector z prime, in fact, has a small L1 norm. So that shows that you can, in fact, produce good vectors. That's the end of this argument. Okay. Let me conclude with some open problems. So the first open question is to obviously try and think whether you can extend this better than 1/2 approximation algorithm for max cut to a rich family of graphs. So for example, can you extend this to all bounded degree graphs? Can you do this for graphs with small threshold rank? Stuff like that. The other question I'm interested in understanding is whether you can show lower bounds for testing free colorability on expanders. So there is already some work by Pan and Yuichi on this in Soda last year. But here what I'm interested in is the following situation. Here I'm trying to shoot for a very large gap. Right? I mean, the gap is, so take any graph, if you look at the free colorability value of that graph, it's going to be at least 2/3. Just take a random coloring. That suggests that you can always satisfy 2/3 of the edges. So here I am shooting for the largest possible gap. So that's a question. And a bit more generally, I'm interested in understanding whether the notion of approximation resistance that was recently shown in streaming, can be extended to the sublinear world as well. Can you have approximation resistance for approximating two CSPs even on expanders? So that would be nice thing to see. So that's all I have. Thank you, but just hold on a moment. So the spectral claim that I recently showed, that was actually a homework problem that Luca Trevisan asked once in his Sweden summer school. And I learned spectral graph theory really from lecture notes of Luca Trevisan. So it's in his honor.
Any questions, comments?
applies to unbounded degree graphs?
No, it does not. We crucially need, so in fact, even that spectral claim that I showed you, it requires the graph to have bounded degree.
Okay.
So it also works for regular graphs. So it's a weird thing. Even if your graph has unbounded degree, but it is regular, that spectral claim goes through. But if it's bounded degree, then there is a bunch of like things you have to handle, and that degree parameter gets in the way.
Yeah. And other questions? Yeah.
Have you thought of geometric graphs?
Not yet.
Sorry, I have one more question. So all your algorithms require like square root of basically n to the 1/2 plus something, right?
Yes.
Is there like a reasonable class of graphs where potentially you could get just square root of n? Or?
So I mean, already like Michael and others showed that you must pay up running time strictly more than root n. But so for
Does it apply to expander graphs, or is it like
it applies for expander graphs. It applies for expander graphs. For planar graphs, I think you can do better. Like maybe Pan might even know such a result of the top of his head. I believe partition oracles already give you that, right?
So for planar, you can get a two-thirds approximation by just the number of edges, which we discussed several days ago.
Oh, okay, okay, yeah. All right.
Any other questions? Okay, let's thank the speaker again.